Okay, so now that we've talked about the definition of a vector space, we've run through some examples. I want to look at some other examples of things that could be called vector spaces, but might seem a little bit unusual. And in fact, we're actually going to start with a non-example, something that is not actually a vector space, but appears like it could be. Now, I'm going to define this set as the set of all ordered pairs of real numbers, but notice I'm calling it V, I'm not calling it R2. And the reason for that is because the notation R2 is now going to be reserved for the vector space R2, not just the set of ordered pairs of real numbers. And remember, the difference between those two things is that a set simply has objects in it. A vector space includes a set, but it also includes those operations that we define on it, addition and scalar multiplication. So whenever I use the notation R2, we want to be thinking of it as the vector space of ordered pairs of real numbers with the usual definition for addition and scalar multiplication. Here, I'm going to be defining addition differently, so I don't want to call it R2, I want to give it some other name. Okay, V is a set of all ordered pairs of real numbers with the following operations. I made a typo here, so I wrote in the fix after printing it. Here's where this looks different from R2. A1B1 plus A2B2 is defined this way. Now, normally, if I added these two ordered pairs, I'd be doing A1 plus A2 for my first component, but instead, this operation multiplies those two components. B1 plus B2 is still going to be my second component. So this first component is the only thing that actually changes. Notice that scalar multiplication is still defined the usual way. So it turns out that by messing with this addition operation just a little bit, this thing will no longer be a vector space. However, it still satisfies some of the properties of a vector space. So for example, we can show that V has a zero vector. Okay. Now, how do we find that zero vector? We don't, you should be able to see that it's not the vector 0, 0 anymore. That would actually mess this thing up. So let's take some vector A, B, and if this thing has a 0 vector, I don't know what it looks like yet, so I'm just going to call it x, y. And I want to show that if I select x and y carefully, the result should be A plus B, or sorry, AB. That would make this thing the 0 vector because adding it to AB didn't change it, okay? But what does that actually mean if this is true? Well, when we add two vectors in this vector space, the rule is we multiply the first two components together. So AX is going to be the first component of this vector, but we want that to be the same as just A. And then B plus Y should equal B. Okay, because that's how we define addition for the second component. You just add those, but you multiply these. All right. Now, if we want this to be true, I can see then x would have to equal 1. And if this is going to be true, I can see that y would have to equal 0. So that means my 0 vector in this set is the ordered pair 1, 0. Notice it's not 0, 0 like we would have expected. And that's because if it were 0, 0, then my first component here under this addition operation would always come out to 0, even if A was something other than 0. Okay? So my 0 vector looks different. But remember, I need to show that this is not a vector space, which means I need to show that it fails one of my vector space axioms. Now, it may fail several of them, but that's not really important because if it fails any one of them, then it can't be a vector space. So I just need to find one that doesn't work. Let's go back to our set of axioms, and let's pick one to try. Let's say Axiom 9. This one where we're multiplying by two scalars. I want to show that this one fails. So let's pick a vector in this set, or an object in this set. Let me call it xy. And actually, let me back that up. I'm going to stop myself here. Okay, now why? Well, I jumped to Axiom 9, but I'm realizing that's actually not a good idea. And the reason for that is because Axiom 9 only concerns scalar multiplication here. Okay, now if I look at the definition of my vector space, scalar multiplication was defined in the exact same way that we define it in R2, which is already known to be a vector space. So any property that only involves scalar multiplication, I should expect to be satisfied by this vector space. Instead, I should look for a property involving addition, since that's the one thing that makes this set different from R2. So let's back that up. Let me look at Axiom 7. It actually involves both scalar multiplication and addition, but that's my distributive property. Okay, so let's suppose I'm looking at k times the sum of two vectors or two elements of this set. Let's call them x1, y1 plus x2, y2. Okay, now under the definition of addition in this space, this should be equal to k times the vector x1, x2, y1 plus y2, which, using my definition of scalar multiplication, which is the same here as it is in R2, is going to look like k x1, x2, and then the k can multiply and distribute into those components there, k y1 plus k y2. Okay, what have I shown? Well, nothing that relevant quite yet. If I want to show that this thing is not a vector space, I need to show that, or I'm going to show that this axiom fails. I've computed this side. I need to show that this side comes out to something different. Okay, so what if I were to evaluate separately k x1, y1 plus k x2, y2. Well, in this case, I'm doing the scalar multiplication first, which again looks like normal scalar multiplication. K x1, y1, k y1 plus k x2, k y2. And now when I do the addition, I'm supposed to multiply these first two components. But the result there is going to be k squared x1, x2, and then k y1 plus k y2. My second component here matches my second component here, but this thing does not match that thing. At least if k is not equal to 0 or 1. If k can be any real number, then I could choose, for example, 2. In this case, I'll have 2x1, x2, and here I'll have 4x1, x2. These should be equal if Axiom 7 is satisfied, but they aren't. So this can't be a vector space for that reason. Okay. Here is another example. This is considered to be a classic example of a bizarre vector space. And most linear algebra courses will show you this one. Now, this vector space isn't necessarily useful. And we're not talking about this because it's useful. We're talking about it because we're just looking for what types of things satisfy the definition of a vector space. Now the vector V, the set V is going to be the set of all positive real numbers, only positive real numbers in this case, and we define the addition and scalar multiplication operations in a bizarre way. U plus V, where plus is the addition operation, is actually going to multiply the two vectors u and v. Remember, these are real numbers. So on this side, this is what we're calling addition, but it doesn't actually look like real number addition. It multiplies the two real numbers. Scalar multiplication is exponentiation in this case. In other words, if I multiply the scalar k times the vector u, which is also a real number, then this doesn't actually look like multiplication. What we actually do is take u and raise it to the power of k. We want to show that this is a vector space. Now, because it takes a lot of time to go through all 10 axioms, I'm not going to go through all 10 of them. All 10 of them are satisfied, but I'm just going to show you 3 of them. These 2 your book shows you, Axiom 4 and Axiom 5, and I want to show you this as well because it shows you that under this definition, the 0 vector doesn't necessarily look like 0, and inverses don't necessarily look the way that you think they would. Axiom 9 is not in your book. I'm going to just prove that here to give you something different to look at. So let's suppose U is an element of V, and let K and M be scalars. So first of all, Axiom 4 says that we need to find a zero vector. And notice, under this definition, if I do 0 plus V, I don't get V, unless V is also 0, because 0 plus V actually means 0 times V, which will be the real number 0. It doesn't leave me with V for all values of V. So, but it's easy to verify that the number 1 functions as a zero vector here, because if I add 1 to a vector u in either order, 1 plus u or u plus 1, then in either case, it's actually interpreted as multiplying u by the number 1, which gives me u. Notice 1 plus u is equal to u. Don't let that throw you. Again, this is not the same addition that you're thinking it is if you're just working with real number addition. So the number 1 is the zero vector in this space. Now let's suppose that u is not equal to 0. In fact, I didn't really need to make this assumption because we assumed up here that v is only including positive real numbers, so it couldn't be 0 anyways. We need an additive inverse. In other words, now that we've identified a zero vector, which is the number 1, then I need to show that for every element of v, I can find another element in v such that when they're added together, I get that zero vector. I get the number 1. Well, the choice that's going to work here is the reciprocal of u. And this is why I actually assumed u was non-zero, but again, didn't need to make that assumption. It was already implicit. What happens when I do u plus the reciprocal of u? Well, in either order, our addition operation technically multiplies those two things together. And u times whenever u is equal to 1, but that's what our zero vector is. So this gives me the zero vector, which makes 1 over u the negative or additive inverse of u. Okay, not what you would have expected. Axiom 9, this is the one that says that if we have a scalar times, then in parentheses a scalar times a vector, it's the same thing as the product of the scalars then multiplied to the vector. To do this one, remember k and m are interpreted as scalars here. U is an element of v. What does it mean to multiply by a scalar? Well, under our definition, mu means u to the mth power. Okay, this produces some other vector in v. And then if I multiply that by the scalar k, under our new definition of scalar multiplication, I'm actually taking this entire quantity and raising it to the power of k. Here's where I can use an exponent property. I know that this is a power to a power. This is the same thing as u to the km. However, u to the km is the same thing as taking the constant km and multiplying it to u using this scalar multiplication that we've defined. So that proves that property. The other 7 properties can be proven as well, and it's a good exercise to try that. This is a very unusual vector space, and again, it's not necessarily one that we would ever have a practical use for, but its purpose is to show that vector space, the concept of a vector space is a very general one, and not every vector space has to look the way you think it has to look. Okay? All right, we're going to end this section with a theorem, and what I want to do is before I talk about that, talk about a little bit more about why generalization of this type is so important in math. We've shown here that we have this definition for a vector space, which again, a set of objects with 2 operations, addition and scalar multiplication, satisfying these 10 properties. We've shown that several familiar and even a couple unfamiliar sets and operations fit this description. So there are already a lot of things that we can call vector spaces, and there's going to be even more that we talk about in 4.2. So what's the benefit of generalizing then? Well, if we can prove general theorems about vector spaces without having to specify any particular vector space in that theorem, then the result will apply to everything that can be called a vector space. Okay? And this theorem right here is one such theorem. So here, let's let V be a vector space. U is going to be a vector in V, and K is going to be a scalar. I have these 4 properties here. Okay, this first property says that if I multiply u by the scalar 0, then the result is the 0 vector. This here says that if I multiply the 0 vector by any scalar k, then the result is the 0 vector. This property says that if I multiply any vector by the scalar -1, I get the additive inverse of u, or I get the opposite of u, negative u. And here, this one says if I multiply k, a scalar k times a vector u, and if the result is the 0 vector, then one of those two quantities had to be 0. Either k was the scalar 0 or u was the vector 0. We've seen this property specific to vectors in Rn already. Now you might look at this theorem and say, well, this is the most obvious theorem. I know that if I multiply something by 0, I get 0, right? And I know that if I multiply something by -1, I get the negative of that thing. But the thing is, you don't know that. You know that for specific vector spaces. You know that to be true for real numbers. If you multiply a real number by another real number, if you multiply a real number by 0, you always get 0. If you multiply a vector in Rn by the scalar 0, you know that you get the 0 vector in Rn. Similar for matrices. But it's very, very common when you're first getting used to this level of abstraction to assume way too much. Remember, this is a general vector space. We have no idea what it looks like. And in fact, we just talked about a very bizarre vector space where this 0 is actually the number 1. So how do we know that this should be true in any vector space? Well, right now, the only tools that you have at your disposal are those 10 vector space axioms. That's the only thing that you can use when proving a theorem like this. Your book proves A and C, and I would highly recommend you go into your book and look at those two proofs because they're very, very important. It's very, very important to see how those steps are laid out. Because they're already in your book, I'm going to prove a different one. I'm going to go ahead and prove B, which says that if you have the 0 vector and you multiply it to any scalar, the result is the 0 vector. Okay? So I'm going to say let k be a scalar. And then I want to investigate k times 0. Now remember, the only thing that I get to assume about the 0 vector is that it acts like an additive identity. In other words, if I add it to any other element of V, then it doesn't change that element of V. Well, what if I were to add the 0 vector to itself? 0 plus 0 should still be 0, and notice that that's just straight from the definition of what the 0 vector is. Okay, so here I'm using one of my axioms, Axiom 4, in fact, which defines the way that the 0 vector works. Then I have another axiom, Axiom 7, that says that I can distribute scalars over vector addition. So because I have an axiom that allows me to do that, I can say that this is equal to k times the 0 vector plus k times the 0 vector. Now, at this point, I have no idea what k times the 0 vector looks like. The theorem says that this k times the 0 vector should equal just the 0 vector, but I don't know that yet, so I can't use that. Instead, I have to just go with the fact that V is a vector space, and vector spaces are closed under scalar multiplication, which means k times 0, whatever it is just some other vector in V. And because V is a vector space, all of the vectors contained in V have an opposite, or an additive inverse. So whatever k times 0 is, there's another vector that I call negative k times 0, and this functions as an additive inverse. So if I were to add this to both sides of this equation here, I get negative k0 plus k0 equals negative k0. Now notice the parentheses here. It's because I'm adding a quantity to a sum that was already there. So the assumption is that this sum would have been performed first. Okay. Now, using the definitions in my axioms, I'm adding a vector to its opposite here. By definition, by that axiom, Axiom 5, I believe it was, this needs to come out to the 0 vector. Okay. Over on this side, I would like to get some cancellation as well, and I can do that by regrouping my parentheses. Rather than have the parentheses here, I can regroup them over here. That's the associative property of addition, which is Axiom 3. Now, I know that this sum is going to be performed first, but as was the case here, because I'm adding a vector to its additive inverse, that gives me the 0 vector. And then finally, by the definition of the 0 vector, what's left on the right-hand side is just going to reduce down to k times the 0 vector. That is what I was trying to prove. Now, again, you might look at this and think that's totally overkill. This should have been obvious, but no, it should not have been obvious. Because again, you have no idea what the vector space phi looks like. You have no idea what its 0 vector looks like. So things that used to be obvious are no longer obvious. But every single step of this proof only used things that I was allowed to assume about V, and that is these 10 vector space axioms. Now, if I wanted to be really careful, I would have written in which axioms I was using where, but I chose instead to kind of talk through it. Make sure you understand how this proof worked. And now that we've proven that property, and we're going to go ahead and take the other 4 or the other 3 as proven, we can say that this would be true in any vector space at all, not just the ones that we're familiar with. That's the power of abstraction and generality in this level of math. Okay, that's it for 4.1. Next section we'll be dealing with subspaces.